Hi everyone, my name is Webster and I'd like to talk about universal fault-tolerant quantum computing with Stabiliser codes. This is joint work with Michael Vasmer, Thomas Scruby and Stephen Bartlett and can be found in this archive reference. I'd like to begin by talking about the motivation for this work. Specifically, there are two conflicting stories often told about fault-tolerant quantum gates. Firstly, it's often said that realizing a universal set of gates fault-tolerantly is really hard. The main evidence presented to this is the famous Easton-Nil theorem, which shows that transversal gates, that is the standard approach to fault-tolerant gates, are not sufficient to realize the universal quantum computing in any quantum error correcting code. However, this is just one of many other no-go theorems that have been introduced in the years since, more even than I could list here. Taken together, these are suggestive of a landscape where realizing a universal set of gates fault-tolerantly should be extremely difficult, and it should be a major problem how to solve this. However, one could also note that we know of many ways to realize a universal gate set fault-tolerantly. The main evidence presented for this story could be magic state distillation and injection, which remains the main approach to circumventing no-go theorems such as those on the left. We note as well that this approach actually predates no-go theorems such as the Easton-Nil theorem, again reinforcing that perhaps realizing a universal set of gates doesn't seem so hard. On top of magic state distillation, though, there have since been a plethora of other approaches as well suggested that also allow us to realize a universal gate set fault-tolerantly. Taken together, these approaches, and many more that I haven't had room to list, suggest a landscape where realizing a universal gate set fault-tolerantly is almost too easy, and there are almost too many ways that we could do it. The motivation of this work, then, was to make sense of this situation. In particular, we first wanted to ask the question of whether we can unify the no-go theorems on the left. Is there some underlying principle which we can develop, which encapsulates the origin of all of these no-go theorems, and really develops out in what sense realizing a universal set of gates fault-tolerantly is hard? Secondly, can we unify these schemes for realizing a universal set of gates fault-tolerantly? Are there underlying principles or is there an underlying framework that we can use to derive all of these approaches and more, and which gives us an approach that can be taken in general to design universal fault-tolerant quantum architectures in broader contexts? Finally, can we reconcile these apparently disagreeing stories? Can we understand how it can be that on the one hand, it seems that realizing a universal set of fault-tolerant gates is hard due to these no-go theorems, and yet also we have so many ways to achieve it, suggesting that it's actually not so hard after all. To understand how our work addresses each of these questions, I'd like to give a big picture overview of what we showed and what I'm going to talk about today before I go into more details. In particular, we begin by considering what it means for a logical operator to be fault-tolerant, and in particular argue that a natural notion of fault-tolerant operations is local noise-preserving quantum channels. We show that such quantum channels necessarily are limited in the extent to which they can spread errors, and that this implies that they can't be universal for quantum computing on a range of standard stabilizer codes. Taken together, these form a no-go result, which can be understood as a generalization of results such as the Easton-Nil theorem for the codes to which they apply, and which we argue encapsulate the underlying principles behind the understanding that fault-tolerant quantum computing on a universal basis is difficult. However, it also points the way, because of its generality, to allow us to understand how in general it can be circumvented. In particular, it clarifies a natural generalization of local noise-preserving channels to the class of essentially local noise-preserving channels, a more general while still fault-tolerant class. We showed that unitary essentially local noise-preserving channels are still constrained by our no-go theorem, but that introducing non-unitarity by incorporating error correction into the implementation allows us to develop implementations that can only spread correctable errors by some limited amount, while spreading uncorrectable errors, in particular logical operators, by an unbounded degree. And we show that this naturally leads us to two classes of approaches to realizing a universal gate set: intrinsically fault-tolerant implementations, such as state injection and code switching, and interspersing error correction throughout the implementation of a logical operator, which leads to gradational approaches such as code deformation and peaceable fault tolerance. Taken together, this provides a general framework for circumventing no-go theorems, which we believe could be useful not only in these situations we've considered to bring order and clarity to existing schemes, but could also motivate future schemes and progress in important areas such as fault-tolerant gates on LDPC codes, where at the moment progress is held back by a lack of general understanding of how to proceed. Let's now talk through these ideas in more detail. I'd like to begin by going back to this question of what fault tolerance means. In particular, we consider fault-tolerant logical operator implementations. A logical operator implementation is a quantum channel, that is, some operation that acts on the physical qubits of an error-correcting code, and is such that the channel acts as the logical operator U-bar on the logical space, that is, the code space. However, importantly, the action of logical operator implementations in general on error states, that is, states that aren't in the code space or logical space, is not constrained by the logical operator implementation. Instead, this is constrained by the requirement of fault tolerance. Fault tolerance requires that we have a benign action on error states, so that error states do not become overwhelmingly damaging to the processing of information throughout the process. More specifically, we require that fault-tolerant operations should map tolerable noise to tolerable noise. By tolerable noise here, we mean noise models in which error correction can proceed to a satisfactory extent. More precisely in our work, we consider tolerable noise to be noise where we can do error correction with an error correcting threshold, meaning that below some noise rate, we're able to achieve arbitrarily low logical error rates by using a larger and larger code size or code distance. The motivation then for why we need to consider fault-tolerant logical operator implementations is it ensures that in a setup where we have a quantum memory, that is a quantum error correcting code, that functions in the presence of our noise, that it continues to function even as we apply fault-tolerant even as we apply logical operator implementations to process the information encoded in it. In particular, we consider a particular context in which tolerable noise is relevant. That is, we consider tolerable noise in this context to be local stochastic noise, meaning stochastic noise where the probability of errors decays exponentially with the size of the errors. This is a relevant regime since significant fault tolerance work has been done with local stochastic noise, and a number of threshold theorems have been proven for classes of codes such as concatenated codes, topological codes, and LTPC codes. This means that it's common to work in a regime where we assume that that local stochastic noise is tolerable and choose codes accordingly. We thus consider fault-tolerant logical operator implementations with respect to local stochastic noise. These, therefore, are local noise-preserving channels, which we define to be quantum channels that map local stochastic noise to local stochastic noise. In particular, then, throughout at least the first half of this talk, we'll consider the class of fault-tolerant channels that we consider to be those that are local noise-preserving. Local noise-preserving channels, as we show in the paper, are highly general and include standard approaches to fault-tolerant gates, such as transversal gates, locality-preserving gates, braiding defects, and constant depth quantum circuits, among other approaches. And so this general notion of fault tolerance really encapsulates a wide range of previous approaches and goes beyond them. That previous slide was quite abstract, so let's look at some of the intuition that helps us understand local noise-preserving channels. The key fact that we show, which allows us to make progress, is by relating the property of being local noise-preserving to the extent to which errors are spread by the action of a logical operator implementation. Specifically, it's commonly understood that a fault-tolerant operation is one that doesn't spread errors too much. We show that indeed, this is a necessary condition for a channel to be local noise-preserving. Specifically, we define the spread of a Pauli error P under a quantum channel A in this way. The spread is the ratio of the size of the support of the image of P under A to the size of the support of P. That is the factor by which the support size of P is increased by the action of the spread of the operator. As an example then, transversal gates, such as a Hadamard acting as a tensor product in each qubit of a code block, have small spread. For example, if we have an X error afflicting one qubit of a code and apply a transversal Hadamard, this will transform to a Z error afflicting that qubit, but not spread the error to more physical qubits. This means that the spread, according to this formula, is simply 1 for this. This is in fact general for transversal gates. Transversal gates on single code blocks always have a spread of 1. Similarly, locality preserving or constant depth quantum circuits have the property that they have spread that is in some way restricted or limited by the size of the circuit or the degree of non-locality. By contrast, a generic logical operator implementation will generally involve entangling a physical qubit with many other qubits of the code. This can allow, for example, a physical X error on one qubit to spread to an error afflicting all n qubits of the code, such as in this example. The spread of a channel of this kind would then be n, or some large factor, where n is the number of physical qubits in the code. The takeaway then is that general approaches to logical operator implementations will spread errors by a large amount, and that this in general will mean they won't be fault tolerant, since they'll give rise to potentially very damaging errors. While nice fault tolerant approaches such as transversal gates have very limited spread of errors, fitting our intuition. We precisely define a quantum channel to have bounded spread if for all Pauli errors P, the spread of P under A is bounded by some constant independent of the code distance. In particular then, with this definition, we show as theorem 1 that local noise preserving channels necessarily have bounded spread. This is important since we also show that the spread of a quantum channel constrains its ability to complete a universal gate set. In particular, the basis for this is noting that in the case where the ratio of the image of a logical operator P bar under the action of U bar over the support of P bar goes to infinity as the code size increases, then U bar does not admit a bounded spread implementation. The reasoning for this is that if P bar is matched under U bar to some much larger operator U bar P bar U bar dagger, then this much larger operator will involve a large spread of Pauli operator P bar, and this large spread will preclude it having bounded spread. As an example, let's look at the three-dimensional surface code. The three-dimensional surface code has a logical X operator supported on a plane and a logical Z operator supported on a line. This means that the ratio of the support sizes of logical X and logical Z scales with the code distance, this linear extent of the code, which goes to infinity naturally as the code distance increases. This implies that we can't have a bounded spread Hadamard operator, since a Hadamard operator would need to map logical Z to logical X, which we can see would involve spreading this logical Z line out to a whole logical X plane. The fact that we can't realize a logical Hadamard on the 3D surface code, in fact, turns out to be what precludes a universal set of bounded spread gates on such a code, since we can, in fact, realize a non-Clifford gate, such as the control-Z gate. As a second example, we can consider the two-dimensional color code. The two-dimensional color code has a logical X operator supported on a line, while the Clifford phase operator logical S is supported on the whole of the code. This means that the ratio of the support size of XS to logical X again scales with the code distance and goes to infinity as the code distance increases. This means that we can't have a bounded spread logical T gate on such a code, since the T gate maps X to XS. Again, this is consistent with the understanding that implementing non-Clifford gates in 2D codes cannot be done by standard means. Indeed, we show in general that it can't be done by bounded spread channels. We prove our main no-go result then by generalizing these examples to a larger context. Specifically, our theorem 2 is that bounded spread logical operator implementations cannot be universal on B-constrained stabilizer codes, where B-constrained stabilizer codes, as we'll discuss in a moment, are a large class of stabilizer codes, defined such that they have the property that this theorem applies to them. In particular then, since we showed that local noise preserving channels necessarily have bounded spread, the following corollary naturally follows that local noise preserving logical operator implementations cannot be sufficient for universal quantum computing on B-constrained stabilizer codes. This corollary constitutes our main no-go result, and we can see how it generalizes important earlier no-go results such as the Easton-Nil theorem on B-constrained stabilizer codes. In particular, as we've discussed, this notion of local noise preserving logical operator implementations is a much more general notion of fault-tolerant gates than previous work that's focused on examples such as transversal gates or locality preserving logical operators. So this no-go result precludes universality in a very broad way in fault tolerance, rather than simply for specific classes of gates. As discussed, B-constrained stabilizer codes have a very technical definition, which we constructed to encapsulate the property necessary for this no-go result to hold. However, we note that, as we show in the paper, a number of important classes of the most standard, well-studied stabilizer codes are indeed B-constrained. For example, B-constrained stabilizer codes include all conventional topological stabilizer codes, that is all topological stabilizer codes with TQFT order. This includes all of the most standard examples, such as all two-dimensional topological stabilizer codes, as well as surface and color codes in all dimensions. We also show that concatenated stabilizer codes are another example of B-constrained stabilizer codes. It's quite plausible that much larger classes of stabilizer codes are also B-constrained. For example, it could be the case that larger classes of LDPC codes or tensor network codes such as holographic codes are also B-constrained. We note that whether this is the case or not constitute interesting open questions, since on the one hand, if it is the case that these codes are B-constrained, it would greatly extend the scope of our no-go results. While conversely, if it turns out that either of these examples are not B-constrained, it may turn out to be the case that it's possible to circumvent our no-go result, and indeed, many of the famous no-go results for fault-tolerant quantum computing by different means. For example, there may exist a universal set of banded spread gates for such codes. We leave this as an open question, but encourage further study. In summary then, the logic of our no-go result is as follows. We associate fault-tolerant quantum channels with the general notion of local noise-preserving quantum channels, and show that such quantum channels necessarily have banded spread of errors, which implies that they cannot be universal in a large class of standard error-correcting stabilizer codes. Understanding this no-go result points the way for us to then understand how it can be circumvented, which is how we can allow ourselves to have a general framework to allow such no-go results to be circumvented, pointing the way to general design of universal fault-tolerant architectures. Specifically, the important fact we observe is that the action of quantum channels on uncorrectable errors does not affect their fault tolerance. This is because uncorrectable errors must be highly unlikely in any tolerable noise model. Thus, it's the case that a quantum channel that fails to be fault tolerant must fail to be fault tolerant because it maps some set of correctable errors to uncorrectable errors, and not because of its action on the extremely unlikely uncorrectable errors. This naturally gives rise to a generalized notion of fault tolerance then, essentially local noise preserving quantum channels, which are those such that the restriction of the channel to the set of correctable errors is local noise preserving, but the action on more general errors, uncorrectable errors, is unconstrained. We show that unitary essentially local noise preserving quantum channels still have banded spread. Specifically, what we show is that if a unitary quantum channel has unbounded spread on any Pauli error, it necessarily has unbounded spread on some single qubit Pauli error. This is because the action of a unitary on the product of errors is equal to the product of the action on the individual errors. This means that generalizing local noise preserving channels to essentially local noise preserving channels does not allow us to circumvent our no-go result with unitary operators, that is, operations that act as unitary operators on the physical qubits. This is interesting since it justifies the intuition that many would have that non-unitarity plays an essential role in all of the tricks used to achieve universal quantum computing. In particular, what we show is that we cannot circumvent our no-go result with unitary, essentially local noise preserving channels, but we can by using non-unitarity in a specific way. That is, by incorporating error correction into the implementation of logical operators. The important property that this has then is that it means that correctable errors remain bounded in the extent to which they can be spread, since the error correction incorporated into the operation prevents their spread by correcting them. While on the other hand, logical operators, an instance of uncorrectable errors, can have unbounded spread since they're left unchanged by the error correction steps, and thus are allowed to transform. For example, the logical Z we saw earlier in the 3D surface code could grow to be a logical X in the 3D surface code, without a corresponding growth and correctable errors that would cause it to fail to be fault tolerant. This insight then is what allows us to construct our approaches to generally circumventing no-go results to realize universal fault tolerant quantum computing. The challenge is that incorporating error correction into such implementations is difficult, as it's not sufficient simply to perform error correction before and after an unbounded spread operation. This is because errors that occur at the beginning of the implementation could then, in that case, be spread to unbounded, uncorrectable errors by the end of the operation. However, we note that there are two general approaches in which we can incorporate error correction in the necessary way, and that these give rise to two classes of schemes for circumventing the no-go result, which encapsulate most of the previously proposed schemes for realizing universal fault-tolerant quantum computing. Firstly, we note the concept of intrinsically fault-tolerant implementations. These are based on doing error correction by teleportation, which was proposed by Emmanuel Nil some time ago. In particular, performing a teleportation circuit with an ancillary logical bell state like this has the effect that the logical state psi is mapped to logical state psi on a different qubit, but with error correction performed along the way. Specifically, this error correction arises in these steps where we perform logical measurements and corrections based on these logical measurements. The key value of this kind of error correction in this context is it allows us to implement gates simultaneously with the error correction. This gives rise to the well-known phenomenon of gates done by teleportation proposed by Gottesman and Trong. Specifically, this can be done by this circuit here, where we see that this logical U applied to the second qubit of the ancillary state and then throughout the last wire of the code allows us to get a state psi bar mapped to the state U bar psi bar, which has also been error corrected along the way. We note that in fact, while these circuits up here are general, it's possible to simplify them in the case of CSS codes where only one kind of error is spread, either X or Z errors. And we note these circuits since they're the form that are often used in these universal schemes. There are two main classes of examples of intrinsic fault tolerance that we discuss, and we see how they correspond to a highly important range of approaches to realizing universal quantum computing. Firstly, we have state injection, whereby some ancillary logical state is prepared and injected into the scheme by teleporting the logical state onto the wiring containing the ancillary state. The most well-known example of this is magic state injection, where some magic state, such as this T-bar plus bar, generally prepared by a process such as magic state distillation, is injected to allow us to perform a non-Clifford T-gate that can complete a universal gate set on codes such as the 2D surface code. However, other forms of state injection are also important, such as coherent state injection, where, for example, a logical plus state can be injected to allow us to perform a logical Hadamard gate, which can be useful, for example, on the 3D surface code, where the logical Hadamard completes a universal gate set. We note then that both of these circuits can be understood as variations on the error correction by teleportation circuit, where the respective gates, T-bar and H-bar, are applied throughout the process to allow their implementation fault tolerantly. Secondly, we note that code switching can be understood as an example of an intrinsically fault-tolerant logical operator implementation. Specifically, teleportation can be used to map a logical state from one code to a different code. This is useful since if the two codes together have a universal set of banded spread logical operator implementations, then we can realize such a universal gate set by switching between the codes using this teleportation circuit as required to do different gates. This teleportation circuit then can be understood as one interpretation of code switching, which can also be adapted to different approaches such as gauge fixing or dimensional jumping, which nonetheless retain the same intrinsically fault-tolerant structure. The alternative approach that we note that can be taken to realizing, to circumventing our no-go result to realize a universal set of fault-tolerant gates is gradational logical operator implementations. These are based on the principle of taking a unitary implementation of a logical operator, for example, this A, and decomposing it into a sequence of banded spread steps. In general, this number of steps T will be unbounded in the code size to allow us to realize an unbounded spread gate by a sequence of banded spread gates. The idea is that this allows us then to intersperse error correction between each time step, as done by these channels Ki, which are non-unitary. The idea then is between each error correction step, only a banded spread channel is applied, which means that we can correct errors before they're allowed to spread too far. We note the most natural example of gradational logical operator implementations is code deformation. This is where we interpret each AI to map us between a sequence of error correcting codes, since it changes the stabilizers to different operators. We can then perform decoders on these intermediate codes to give ourselves fault tolerance by slowly deforming between the sequence without ever allowing the errors to become uncorrectable. This works provided that we have intermediate codes where the noise remains tolerable, and that we have some decoders that we can do on these intermediate codes. In general, finding decoders for the intermediate codes can be challenging. However, there are specific contexts where it can work well. A famous one is braiding defects. However, braiding defects is known to not be universal, which we confirm in our work by showing that in fact it has banded spread. However, we do show an example where you can code convert or dimensional convert, meaning perform code deformation between two codes of different dimensions to allow for something analogous to code switching. In this example, we can deform from a 3D surface code to a 2D surface code by going through a sequence of codes supported on rectangular prisms. This allows us to realize non-Clifford gates in the 3D code and Clifford gates in the 2D code. This code deformation example is really interesting because we show in the paper that it can also be generalized to higher dimensions. For example, the 4D and 6D surface codes, which also have a universal set of gates between them. These codes are interesting since they're self-correcting, meaning that instead of performing active error correction, we can allow dissipation to relax us back to the ground state of a Hamiltonian to naturally perform error correction, to self-correct. We showed that our scheme then allows us to switch between the 4D and 6D codes with self-correction at all stages in such a way that we can realize a universal set of gates fault-tolerantly without ever doing active measurements or active error correction. This disproves the common notion, and one that we had going into this work, that classical processing based on measurement outcomes is an essential part of realizing a universal fault-tolerant gate, showing instead that non-unitarity in the form of dissipation of energy in this case is sufficient on its own if it has this error correcting property. We also show that peaceable fault tolerance, whereby we perform some diagonal operation which commutes with Z stabilizers, allowing us to perform correction of X errors, while also not spreading Z errors, such that their error correction can be deferred to the end of the process, can also be understood as an example of gradational logical operator implementations. We note that peaceable fault tolerance is successful on concatenated codes and can be generalized to topological codes by using a just-in-time decoder in the place of the decoder DX and combining it with gauge fixing, which allows us to perform Z error correction. This allows for a non-Clifford gate in 2D surface codes, as shown by Ben Brown, building on work by Hector Bondman. In summary then, what we've seen is that we can prove a highly general no-go result, which encapsulates the general way in which realizing a universal set of fault-tolerant gates is challenging. This naturally gives rise to an understanding of what is necessary to circumvent such a no-go result, leading us to this notion of essentially local noise-preserving channels and ultimately to these two classes of approaches, both based on this principle of incorporating error correction into the implementation of logical operators. We show that this encapsulates a wide range, indeed most, of the existing schemes for universal fault-tolerant quantum computing, and thus can be understood to really unify a wide range of what were previously disparate or ad hoc schemes. With us optimistic that future work could use our work to develop new architectures and new frameworks for fault-tolerant universal quantum computing based on now the deeper understanding we have of why it is that fault-tolerant quantum computing is challenging and how it is that it can be overcome.